Hello, everybody. Thank you very much for joining this session. My name is Yanir Heinik, and I'm the co-founder and CTO of Pixie Holographic Imaging. It's a pleasure to present Pixie to you today. I'll start by exploring the evolution of imaging technology, which has undeniably become an integral part of our daily lives, from taking images on your smartphone through automotive applications, home applications, industry applications. Imaging systems are everywhere. The rapid advancements and widespread adoption of cameras have really transformed the machine vision market, shaping it into the industry that we see today. Despite accomplishments in miniaturization, in ease of integration, in cost reduction, the core physics of cameras have remained virtually the same since the era of film photography. 2D cameras treat light as rays, advancing in straight lines and being focused on a light-sensitive plane, either a chemical film or a photodiode array, to produce two-dimensional images, either in color or monochrome. But that's about to change. Sorry, a small blackout. That's about to change. Pixie's groundbreaking innovation unlocks a new era in digital imaging. Our invention can transform 2D cameras into advanced imaging devices capable of delivering both high-quality color images together with accurate and detailed depth maps. Now let's dive and take a closer look into our technology. Pixie aims at exposing light's wave-like nature. Those waves of light contain information about the color of the source and the distance to it. A Pixie camera looks just like a 2D camera, only instead of focusing light on a color filter array that is common to most RGB cameras, we focus light on a holocoder that is placed on the raw CMOS sensors. Now, this holocoder is a Pixie-designed diffractive optics element. So the raw sensor underneath now records diffraction patterns which encode within them both the color information and the depth information. Then Pixie algorithms analyze these diffraction patterns both deterministically and efficiently, and output the RGB image as well as an IR image and the depth map. So how can this revolutionize the machine vision market? So to answer that, we need to revisit traditional technologies that you treat light as rays and use a color filter array to produce color images. So although these technologies really were the foundation of imaging for decades, they have some inherent limitations to them. For example, imaging in low light conditions, or the absence of depth information, physical depth information in the image. Now, these limitations really impair the ability of 2D cameras to perform complex machine vision tasks like 3D SLAM or object detection and, or 3D modeling, etc. Now, naturally, over the years, advancements have been made to overcome some of these limitations. For example, stereo cameras, as well as structured light or time-of-flight devices, can add valuable depth information, but they have limitations too. For example, imaging reflective surfaces or under ambient light conditions, but above anything else, they really add to the overall complexity and cost of the system. So the only way to truly revolutionize the field is to eliminate its trade-offs, and this is what Pixie actually does. So I want you to meet Erez, our system engineer, and Charlie, the office dog. They are the heroes of this medium-range demonstration movie. Both the RGB image and the depth map come from the same Pixie camera. This is how we filmed this movie. This is a key feature of our technology. All the information channels are completely fused and synchronized because they come from the same captured data. Oh, in the next demonstration I'm going to show you of this short-range packing application, although the 2D image is of high quality, you can't really tell if either of the cans are of different height, and the depth image that is, again, natively fused with a 2D image reveals the truth. Two of the cans are of different height. The difference is of 2 millimeters, a few millimeters in this example. Pixie offers a groundbreaking solution for perception, delivering both high-quality depth information together with RGB images on a single sensor from a single snapshot. We are completely agnostic to the underlying sensor or the lens design, making us relevant for any application and any use case. And we are a true drop-in replacement to any existing workflows. I want to thank you very much for listening and invite you to come visit our booth. We have a demo to show you there, and we'd love to see you. Thank you very much.
Thank you, Janir from Pixie.
Yes.
Great. For fairness, one question. Martin, a quick question, please.
Thanks for your talk. Which type of processor you need for post-processing the data?
Okay, that's a good question. As I mentioned, the algorithms are deterministic, not only on the physical sense, they're deterministic also on the processing pipeline sense. So we can actually calculate the amount of operations that are needed for decoding an image, and the magic number is between 100 and 200 operations per raw pixel. Now, how this translates to gigaflops and power consumption and such depends on the sensor resolution and the platform that you're using, but this is Pixie's magic number.